So you might have noticed today I've spent quite a bit of time talking about Nightfall, or other my colleagues have, and we haven't mentioned Starlight yet, which is the other application that EY works on. But we're going to rectify that now, because I have my colleague Lydia Garms, Dr. Lydia Garms here, who's been doing some extra work on Starlight, and it's all to do with composability. And it's very interesting. If you remember Stephanie Locke talking about Epic, and they were very interested in composability because actually you need it. Without composability, you can't build on what you already have. You're always just starting again. So it's actually a vital piece of functionality. And so you have to think, how can I do composability in my application? But I probably shouldn't waffle on. I should probably let Lydia tell us about it properly. So over to you, Lydia.
Thanks, Duncan. So in this talk, I'm going to talk about some new developments that we've got coming up for Starlight, in particular composability for our private smart contracts. And this is going to allow our private smart contracts to actually call each other. So like Duncan said, we can kind of build on what we already have. A brief outline of the talk. So I'll start with introducing Starlight. Like Duncan said, it's the repository that we've created at EY blockchain. And then I'll give a kind of quick status of composability in Starlight right now and what we already have. Then I'm going to take two Starlight zaps and I'm going to show how we can kind of manually change these zaps to allow one to call the other and achieve this composability. Then I'm going to kind of give a quick roadmap for the future of composability within Starlight, and then I'll finish up. So starting off with the intro to Starlight. So a quick disclaimer: don't rely on this talk for any kind of advice, essentially. So introducing Starlight. So Starlight allows to take a Solidity-based smart contract and compile it into an EVM-compatible ZK application. And the idea behind it, essentially, was it was designed to be used by people who have a good, strong background in developing in Solidity and building these smart contracts and the business logic behind these smart contracts, but not so much knowledge about the complex maths that you require to use these zero-knowledge proofs that will be used to make the smart contracts private. So Starlight kind of makes it easy to do that. So how Starlight works is you take a Solidity contract and then you mark it to specify what variables you want to be secret, and from that you will get a Solidity smart contract, which is just the Solidity contract but marked with these like decorators and these markings, and then you can run the Zapify Starlight command to get a complete working zap. So a zap is kind of like a DApp but with privacy, essentially. Zero knowledge proofs. So these are kind of a really core part of Starlight. This is how we achieve our privacy. So they consist of a prover and a verifier, and the prover actually can prove a relation to the verifier about something. And that something that it proves the relation about involves something secret, so the witness, and something public, so that's the instance. So an example of this is, say you want to prove that you know a discrete logarithm, a really common thing in cryptography. So the relation would be the equation, g to the x equals y. The instance would be the witness would be x, and the instance would be g and y, because these are the public elements. So the zero-knowledge property ensures that the verifier actually learns nothing from the proof, except for that the relation is true and satisfied. So ZK snarks in particular are zero-knowledge proofs that are succinct. So the proof is small and verification is fast, which is great for using it in blockchain. So how do we go from our Solidity smart contract with an S to our Solidity smart contract with a Z? So it's really easy. You just have to add in these secret these secret decorators. So you can see in this escrow contract, it's just marked every variable that we want to be secret. So, for example, balance is a state variable, so that's been marked with secret. An amount is also a function parameter, and that's been marked with secret. And we also we support this for local variables as well. We also have this concept in Starlight of unknown and known variables. So I won't go into that too much in this talk, but just to give you an overview. So in Starlight, because our variables are secret, we have to have the concept of an owner, who is the one who knows the underlying secrets. For a known variable, only this owner is able to change the state, so like change the variable essentially. Whereas for an unknown variable, anyone can increase it or increment it, but only the only the owner can decrement it. So you can imagine this could be useful. Say the smart contract is a charity, something with a charity, and one of the variables is the balance of the charity. Anyone could donate to this charity, but only the charity admin could kind of spend this money. Okay, so Merkle trees is another tool that's used in Starlight. So Merkle trees are just binary trees, and you can store data in the leaves, and each node in the tree is just the hash of the two children nodes below it. And the whole of the sort of Merkle tree can be represented just by the root. So the root is just the hash at the very top of the tree. The great thing about Merkle trees is they allow for efficient membership proofs. So if you want to prove that some data is in the tree, you can take the leaf in the tree where the data is stored, you can find the path to the root, and then you just take all of the sibling nodes along that path, and then the verifier can actually recompute based on all of those all those sibling nodes and the leaf. They can recompute the root. And then check it matches the real root, and this is enough to prove membership due to the collision resistance of the hash function used in the Merkle tree. How in Starlight do we hide our secret variables? So the way we do this is we replace the secret variables on chain with commitments. So specifically, we use the Poseidon hash function to do our commitments. And these commitments are stored in the Merkle tree. But before adding to the Merkle tree, we have to prove that these commitments have been generated honestly and have followed the logic in the smart contract. And then say later we want to access that variable, we want to either read or write to it, we provide the path in the Merkle tree to that commitment, and then we just have to prove that the value that we're using actually matches the commitment stored in the Merkle tree. And you can see that the commitments have the format of they're the hash of the state variable ID, which is just some ID. Each different state variable will have its own ID. The value, which is the sort of secret value we want to hide in our commitments, and the public key, because in Starlight we have the concept of owners for all of our variables, so we include the public key of the owner. And we also have the random salt. So this is like a long random string, and it's really important from a security point of view because otherwise, if you didn't have this long random string, you could just try lots of different values until you get a match, and you could use that to kind of break the privacy. But with this salt, that's so long that protects that, essentially. Okay. So now the question is, what happens is when we change the variable? So the commitments are not homomorphic, so we actually have to replace them when the values change. So we add new commitments to the Merkle tree. But what that means is that in the Merkle tree, we have several commitments from various past states. And we need to keep track of the most recent commitment, otherwise you could use an old commitment and no one would know. So the way we do that is with nullifiers. So whenever we create a new commitment, we have to create a nullifier for the old commitment. And then the way that we prove that the commitment we're using is up to date is we just prove that there's no nullifier for that commitment. So the format for the way we compute the nullifiers is we hash again the state variable ID, same as the commitment. then we only want the owner of the variable to be able to nullify it, because they're the only one who should be able to change it. So we have to include the secret key in the hash. And then we also include the salt to tie the nullifier to the commitment. Okay, so how does this Starlight Zap look? So there's 3 main components. So we have the shield contract, orchestration, and the zero-knowledge circuits. So in the shield contract, we still have all of the public code from the original Solidity contract. But we no longer have any of the secret logic that is moved into the circuit of the zero-knowledge proofs. But we do, in the shield contract, verify the proof that all of that logic has been done correctly. And in the shield contract, we also store the Merkle tree for the root. So we also store the root for the Merkle tree of all of the commitments. And then in the orchestration, we actually have the commitment database, which is like a local database, because the users are going to need the pre-images to all their commitments later when they use them again. So that needs to be stored. And it also contains all the API routes and services. OK, so that was a quick intro to Starlight. So now I'm going to talk a little bit about the current status of composability in Starlight. So starting off with what is composability in general for smart contracts. So in Solidity, with an S, we already have composability. So you can call a smart contract function either in the same contract or in a different contract. And this is a really powerful tool, achieves amazing functionality, because like Duncan said before, you can build, you can use these smart contracts to build together. And we want to achieve this exact same thing in Solidity with a Z. And currently, in Solidity, we can call a .sol contract, so a Solidity contract already. So actually, the previous example is an example of this. So this is a Starlight Solidity contract, and it's calling a Solidity contract. And we can't call a Solidity contract from a Solidity contract, with a Solidity with a Z from a Solidity with an S. This is impossible because the Solidity contract is actually not deployed on chain. Instead, we deploy the shield contract. But you could call the shield contract. Obviously, you'd have to input an instance and a proof. In terms of Solidity, we already support internal function calls. So you can call a function in the same contract in Solidity. But we don't support external function calls. So you cannot call a function from a different contract. So the obvious question is, how do we support this in Starlight? OK, so first of all, let's start with how we already achieve internal function calls in Starlight. So roughly how we do this is we just, so this example contract, we have the assign contract, and we have the remove function and the add function, and in here we have remove calling add. So this is internal. It's calling a function in the same contract. So what will happen is we will just include the logic from add in the circuit for remove. And so in the shield contract, when we verify the proof for the remove function, all of this logic will have been verified already, the add and the remove. Then we call add inside the shield contract. But actually, we turn off the proof verification in add. And we only turn it off when it's being called from remove. Because we don't need to verify this again, because it's already been verified when we verified the remove proof. OK, so external function calls. So we can't do the same thing for external function calls. This is because in the previous example, I mentioned that we actually turn off the proof verification for the function that is being called. So, for example, we turned it off for add. And this is only possible for internal function calls, because we can't configure the shield contract to turn off this proof verification for external function calls. The reason for this is because, first of all, we might be calling a already deployed contract, so we can't change that already deployed contract. to tell it to not verify its proof. And even if we could, we wouldn't really want to do that. We don't want, like, this is kind of a security issue. We don't want to be turning off proof verification based on kind of unknown contracts that could be calling it. So yeah, so we can't do the same thing for external function calls. Okay, so now I'm going to show how we can take two Starlight zaps and make them composable, make one call the other. Okay, so this is the assign contract. This is a Starlight test contract. It's a really simple one. Add, you do an increment. Remove, you do a decrement. And this is the one we're going to be calling. Specifically, we're going to call add. And so this is the one that is going to do the calling. This is the buckets of balls shield contract. And you can see it's a Starlight test contract. What it allows you to do is have these like buckets of balls, and you can deposit balls into buckets, and then you can move them between different buckets essentially. So what we've done here is we've added a call to add in the transfer function on the input number of balls. Okay, so how do we allow this? So the obvious thing to do is, well, why don't we just call in the shield contracts? So in the buckets of balls shield contract, we can actually call the assign shield contract. And in this kind of example, I've shown how you first of all need to import the assign shield contract. And then you also need to do the call in the transfer function. But to do the call, you need the proof and you need the instance. So you're going to now input to transfer two proofs and two instances, one for transfer and one for add. Okay, so we don't make any changes to the assign shield contract because this is an already deployed contract. We don't want to be making any changes to this, otherwise we can't use anything that hasn't already been deployed. I'm sorry, we can't use anything that's already been deployed. So now how do we have these two proofs and two instances being input into the transfer function in the shield contract? So we actually can get this from the orchestration. So in Starlight, for each function, we have a function for each function. So for example, for transfer, we have an orchestration function which generates the proof and the instance. So what we can do is get the transfer function to just call the add function. So we have now the add proof and the add instance. And we can just input both these proofs and both these inputs into transfer. Okay, but if we were to just to follow the previous steps, this would actually be insecure. We're not actually checking the inputs to add. So in the smart contract, we've specified that add has to be run on the input number of balls. But a malicious entity, if we were to just do what we've done previously, could instead just input to add any other number, 5, let's say. And that would still be a valid add instance and add proof just based on a different input. So it would run correctly. There would be no issue, but that would be bad because obviously they've subverted the smart contract. So how can we fix this? So the way we fix this is now for every secret input to a function, we input a commitment as well. So we do this in the circuit and the shield contracts. And then we can prove that we've actually input the right commitment. So this is kind of how it looks roughly. So we have in the add.sock circuit, we've changed this slightly so that now for every secret input, we also need a commitment, and we need to check in the circuit that this commitment really is correctly formed. And then in the calling function, so transfer.sock in this example, for every external function call, we need for each input to every external function call, we need to put a commitment in the instance. And then we need to check this commitment is correct. So we need to check that this commitment really is the commitment to number of balls in this context. Okay, and so for the shield contracts, we have in the transfer function, the transfer function will have been input this commitment, and it will put it in its instance, and it will check this commitment really, in the proof for transfer, it will check that this really is the commitment to number of balls when we verify that. Then we will input this to assign shield.add, and then the inside the add function, this commitment will be also put in the instance, and the proof will be verified with that. And because the same commitment is being verified in both proofs, this ensures we have consistency. Okay, so I haven't talked yet about what happens if the function we're calling actually returns something. So that could happen. So in this example, you can see now add outputs some integer, and that integer is assigned to bucket 0. But we have the same potential problem as input consistency. How do we make sure that a malicious user potentially doesn't try and just change the output of add and set bucket 0 to whatever they want? Well, we can do a pretty similar thing. So now in our shield contracts and circuits, we have to output a commitment for the outputs. So in our the functions that are being called, we don't really need to make any changes in the circuits, because we already output these commitments. In the calling circuits, we now need to, for every external function call with an output, we need to put the output inside the witness and the commitment to that output inside the instance. And then we need to check that this commitment is correctly formed. And then we assign the output correctly to whatever we're assigning it to, in this case, buckets 0. Then inside the shield contracts, what we can do is we can run we can call assign shield.add. It will output the commitment. We will so this commitment will be the kind of correct output because this will have been checked in the add proof verification, and then we can put that inside our instance and check the transfer proof, do the transfer proof verification. And because, again, the same commitment is used in the instance for both proofs, this ensures we have the output consistency. OK, so now I'm going to kind of give a very quick overview of our plans for Starlight in the future, including composability. OK, so like I said, we previously already had internal function calls. And we also had the ability to call solidity contracts. I've just showed that we can make two Starlight apps call each other, and we've tested this. And we've included functions with both public and private variables. And obviously, we've also included the input and output consistency, so this is secure. So the next steps is to put this into the Starlight compiler. So we want the ease that comes with Starlight. So you don't have to make all these changes manually. You'll just be able to run Starlight, and it'll be able to automatically make all the contracts composable. Another thing we want to do is we want to transition away from the Groth16 proofs. So currently, we use these, and these have so we want to transition either to universal setup or no setup, because currently with the Groth16 proofs, every time we generate a new Starlight contract, we have to do a new ceremony to generate the setup, essentially. So this is, we want to avoid this, really. And we also have some other exciting Starlight developments on the way, too. OK, so another thing coming soon, also from EY Blockchain, from the Transaction Manager team, led by Wenqing, is Starlight Sandbox. And this is going to make using Starlight even easier. So you can write a Solidity contract and add decorators to get your Solidity contract. You can also compile and deploy the Solidity contract and expose the API endpoints for the Zap. And then you can use these API endpoints to interact with testnets. And this is going to make setting up proof of concept Zaps easier and faster. OK. So that's all from me. So just to sum up, Starlight currently supports internal function calls, Solidity contracts, but not external function calls. But achieving both would be great, because this would allow the full power of composable smart contracts with the privacy and the ease of Starlight. And we can actually achieve this by enabling the shield contracts to call each other, but we need to enforce input and output consistency for security reasons. So composability in the Starlight compiler is coming soon, so watch out for it. It's on its way at some point. And yes, so thank you very much for listening to me, and please let me know if you have any questions.
Oh, thanks very much, Lydia. That was great coverage of using composability in Starlight. We've got time for a few questions, and there are a few. So let me pick a few for you. So one is, so the first question is asking about what's the difference between the commitment for known and unknown variables, and how does it differ? I think you covered known and unknown variables.
Yeah. So briefly, so how it works is for the known variables, we only have ever one commitment at the same one kind of current commitment at the same time. So we either have a commitments that have already been nullified, and we have one up-to-date commitment with no nullifiers. For unknown variables, in order to increment the state, what we can do is we can allow other users who don't own the variable to create new commitments, and then the owner has access to several commitments, which make up their total kind of state. So say they have a commitment to 5, another commitment to 5, and another commitment to 5, they would have a total balance of 15. And they can nullify all of these commitments to create a new commitment for 15, essentially. So that's kind of the main difference.
Yeah, that makes sense. Yeah. So building on that theme of known and unknown variables, you showed you can do an internal function call with a known variable. And is it the same for an unknown variable?
Yes. So it should be essentially pretty much
just works.
The same thing. Yeah. Exactly. Yeah.
Okay. Right, next question. Do we need to redeploy the Solidity smart contract when another smart contract makes external calls by another function? So I think, if I may just interpret this a little bit, I think what the caller is asking, so you've already deployed one private smart contract and sort of some time ago, and you've got a new smart contract and you want to call that first smart contract. Do you have to redeploy it or do anything like that?
No, you don't. You can just call it using the address. And the one thing is, obviously, we're adding this composability into the Starlight compiler. Sorry, if you want to call a function, like if you want to call a contract that was created before we're making these changes to the Starlight compiler, then yes, you would need to redeploy it, because these contracts will change essentially. But once we have put composability into the Starlight compiler, at that point you can you don't have to redeploy anything. At that point you can call any contract at any time later.
So it's very analogous to a layer 1 normal smart contract in that regard, basically.
Yes, exactly. Yeah.
Okay, brilliant. We've probably got time for maybe one more. So how does return work with a secret variable? Does returning them on chain leak privacy?
No, actually. So the reason is because we do return the commitment and not the secret variable. So although on chain you can see the commitment, this is kept secret because it's within the commitment, essentially. Yeah.
And the commitment just being a hash. So
yeah, exactly.
Doesn't leak any information.
Yeah. Exactly.
Almost by definition.
Yeah.
Yeah. Okay. Right. You mentioned solidity. How is it different from solidity? I think I know what this question meant. You mentioned solidity. How is this different from solidity?
Yeah, so it's very similar. So all you do to create a solidity contract is you just take any solidity contract and you just add the word secret into it, basically. So you take the contract, you add the word secret in wherever you want it to be secret, and you add you might add known and unknown as well to specify what you want from that, and otherwise they're very similar. Yeah, exactly.
Okay, makes sense to me. Lydia, thank you ever so much. That was really informative, and I can't wait to see people doing composed, if that's the right word, private smart contracts. Okay, thank you.